Welcome to today's session of ALPHORES e-learning program. In the previous class, we are discussing about the expansions of liquids, and we have derived an equation for the two types of volume expansions of the liquid, namely a coefficient of apparent expansion and coefficient of real expansion. They are related by the relation coefficient of real expansion is equal to coefficient of apparent expansion plus coefficient of volume expansion of the container or the solid, or we can also write this as coefficient of apparent expansion plus 3 alpha of the solid, that is the container. So this relation we can express in any way. Here gamma r is the absolute property of that liquid. That means whatever may be the container you have taken, coefficient of real expansion will never change. But depending upon the value of alpha, alpha is the coefficient of linear expansion of the container. So in different containers made up of different materials will have different values of alpha. As a result, from this equation, coefficient of apparent expansion is gamma r minus 3 alpha of the container. Very clearly, for different containers, gamma A will be different, but gamma r, it represents the absolute property of the liquid. It remains as a constant in all cases. Now, we have to go for some numericals based on these equations. But before that, as I told you in the last class, we have an application of expansion of liquid combined with the expansion of solids. First, let us complete that, and then we go for the numerical applications of this equation. Now, what is that application is? Generally, we use a barometer to measure the atmospheric pressure. There, we measure the length of the mercury column. The height of the mercury column measures the atmospheric pressure. As we know, the pressure of a stationary liquid column we represent by the equation HdG, where H is the height of the liquid column, D is the density, and G the acceleration due to gravity. But practically, when you are measuring, we express the only of the value of H, because we know the atmospheric pressure is 76 centimeters of mercury. We say like this. Practically, pressure is not measured in centimeter. But out of this equation HdG, we are measuring only the value of H, which is equal to the height of the mercury column in a capillary tube. To measure that height of the mercury column, generally we will be using a metallic scale. Like we will have the capillary tube taken like this. The capillary tube is taken like this, and it is placed in a container. It will be placed in a container to having some mercury. Mercury will be rising. When the mercury is rising, suppose mercury is here. To measure the level of mercury, we are using a scale associated with it. On the scale, you will have the markings. So by measuring the mark of the level of mercury on the scale, we give the reading of the atmospheric pressure in terms of height of the mercury column. In this process, as we are using a metallic scale, yes, we know all the scales are correct only at a particular temperature. At other temperatures, we need some correction. Similarly, suppose you are using the barometer at some high temperature. Because of increase of temperature when compared with the normal room temperature, there will be an expansion of mercury contained in this barometric tube, and also there will be an expansion in the scale, metallic scale that we are using. Therefore, in both the cases, we need some correction regarding the mercury wall expansion and also the expansion of the scale. We have to make some corrections. And how to make this correction to get the true value of the atmospheric pressure even at a high temperature while we are measuring? Then how to measure this? Here, let us consider that case. Suppose at 0 degrees centigrade, I am measuring the atmospheric pressure, and let us assume that at 0 degrees centigrade the scale gives the correct reading. That means the measuring scale or metallic scale you are using it is graduated at 0 degrees centigrade, so that at 0 degrees centigrade it gives the correct reading. Now let the atmospheric pressure represented by the scale is H0. Height of the mercury column is represented by H0. Now I am using this barometer at a place where the temperature is a little bit more, let us say at some T degrees centigrade. At T degrees centigrade it gives a reading, let us say H. H is the value of the reading at T degrees centigrade by the same brass scale or the metallic scale what you are using. Now how to measure the actual value of the atmospheric pressure? Remember, atmospheric pressure, as we said, we can measure as per this equation, whether whatever the temperature, the atmospheric pressure will not change. For you, if you consider a fixed mass of the gas contained in a small container, with the temperature, pressure may change. But atmospheric pressure, there will be no much change with the temperature, so that at all temperatures we can consider the pressure as a constant. And now considering the expansion of the mercury, because mercury also expands with the increase of temperature, let density of mercury at 0 degrees centigrade is D0, and corresponding to this high temperature T degrees centigrade, let the density of mercury is D. Density is also changing. Now how to get the actual reading? Because H0 is correct, but we are measuring the reading at the higher temperature, that is the value of H. This is not the correct reading, because we are measuring on the scale which is expanding as H. Now let us take the equation of the pressure to relate the quantities corresponding to the temperature 0 and the temperature T degrees centigrade. As we measure the pressure to be a constant at 0 degrees centigrade using the level of mercury and density of mercury, we can say H0 D0 into G. In terms of the mercury column at 0 degrees centigrade is H0, density of mercury is D0, now it is G, acceleration due to gravity. So this product represents the atmospheric pressure. But now corresponding to the given temperature, the reading it is representing is H. The measured scale reading is H, and now it is density is now, let us say, D, and acceleration to gravity, because it remains constant, the value of G, it remains as it is. Therefore, because the atmospheric pressure is not changing, both the values are one and the same. But practically substituting these values, H0 D0 equal to H. H is the reading you are taking. But practically what the reading shows, it is not the correct reading. We know the scale is correct at 0 degrees centigrade, but now because of temperature the value will change, but the reading given by the scale is only H. To make a correction, we know the original value, if it is 1 meter, at the higher temperature it expands, so that the actual length that will be represented by 1, you have to add the expansion, so that the final reading is H of 1 plus alpha t, which is the correct reading. It shows H. We have studied about the metal scales. The metal scale may be correct at 0 degrees centigrade, even at 100 degrees centigrade it shows only 1 meter, but practically corresponding to this 100 degrees centigrade temperature it will expand. Even it is expanding by 1 centimeter, actual length is 101, it shows only 100 centimeter, because as we told in the previous classes, the length of the scale appears to be a constant at all temperatures. So when it represents the value of H, it is not the correct reading. It is the reading given by the scale at that temperature. So to get the correct value, we know this reading, but the correct value is H of 1 plus alpha t, because this H into alpha t represents the expansion. So total reading is that value you are showing plus expansion, that gives the total reading or total length of the mercury column. And coming to density, as the temperature increases for the liquids, density decreases. And in the previous classes we studied about the relation between the density at different temperatures. So as per that equation, the density I can write as D0 by 1 plus gamma of T, D0 by 1 plus gamma T, Just you can refer the previous equations to get this relation. So density at higher temperature is d0 divided by 1 plus gamma T. So H0 d0 is equal to, this is the value of H corresponding to the higher temperature, and this is the value of density. Therefore you can remove this term d0, then H0 will be equal to H of 1 plus alpha T, and this is 1 plus gamma T. You take to the numerator, we can write as 1 plus gamma T power minus 1. Expanding this, it is H of 1 plus alpha T. Expanding this binomially and leaving the higher order terms, we can take simply this is 1 minus gamma T. So H0, this is the reading at the 0 degree centigrade given by that scale, and H is the reading given at the given temperature where you are making an experiment. This value we can take, from the reading of the scale of 1 plus alpha T of 1 minus gamma T. Let us expand this. This is H of 1 plus alpha T. Again we have taken this 1 into alpha T, and next one is minus gamma T minus of alpha into gamma into T. In this equation, alpha and gamma, alpha is the coefficient of linear expansion of the scale, material of the scale, and gamma coefficient of volume expansion of mercury. And because these factors will generally in the order of 10 power minus 6, this product will be of the order of 10 power minus 12 or 10 power minus 11, which is negligibly small. So you can neglect the term alpha gamma T, and finally we can express this equation as H of 1 plus alpha T minus gamma T, that we are measuring at the temperature T, and final equation we can express as H0 equal to H of 1 minus, I take minus as a common factor, it is gamma minus alpha of T, and this represents the final equation to get the value of relation between the reading given by the scale at 0 degrees centigrade and the reading given by the scale at the higher temperature H. So by using this equation you can find out the correct value. So this relation is important to find out the correct length of the mercury column, which represents the atmospheric pressure. So this is one important application. Here the basic principle we are using is the pressure, atmospheric pressure remains as a constant irrespective of temperature. This is true only for atmospheric pressure. You cannot apply this condition for any gas taken in a container having fixed mass or fixed volume. But because the atmospheric gas, it will expand in different ways. At any temperature, you can consider the pressure to be a constant, and we are equating these two equations. And finally, that relation is important. Here, gamma is the coefficient of volume expansion of mercury, and alpha coefficient of linear expansion of the material of the scale what you are using in the barometer. So this is one important application. With this application, the relation between expansion of solid and liquid we have used here. Now with this, the application part is completed. Note that this equation is very important. Now let us move on to some numericals related to the expansion of the liquids, and as far as the equation we have studied so far, that is the relation between coefficient of real expansion and apparent expansion as gamma R equal to gamma apparent plus gamma of the solid or gamma of the container. Suppose there is a liquid in a container A, the coefficient of apparent expansion is gamma 1, and in another container for the same liquid, coefficient of apparent expansion is gamma 2. Coefficient of apparent expansion is gamma 2. And let us say alpha of this container is alpha A. Then I want the coefficient of linear expansion of the container value, that is alpha of B I want to calculate. Let me repeat. I have taken a liquid in a container A. In that container, coefficient of apparent expansion is gamma 1 and coefficient of linear expansion of that container is alpha A. For the same liquid in another container, coefficient of volume expansion is gamma 2 and I want the alpha of the second container B. Then how to get it? Now we are talking about coefficient of apparent expansion. We know that coefficient of real expansion is the same in any container because coefficient of real expansion represents the absolute property of the liquid. So whatever may be the container, gamma A may be changing. Coefficient of apparent expansion represents the relative expansion of the liquid with respect to container. It depends upon the expansion of the container. But real expansion is not like that. Real expansion is the absolute property of the liquid. So in any container, gamma R remains as a constant. Therefore, gamma R, let us calculate. It is gamma apparent plus gamma of the container. So it is gamma 1 in case of A plus gamma of this container, because alpha is given, it is 3 alpha A. Gamma 1 plus 3 alpha A. This is coefficient of apparent expansion and this is gamma of the solid, gamma of the container. But if you calculate the value of coefficient of real expansion with respect to the container B, it is equal to apparent expansion is gamma 2 and we want the value of alpha. Let us say it is 3 alpha B. Alpha B we want to calculate. But we know gamma R is a constant, so that whether it is A in A or B, gamma R is the same. So these two are also equal. So you will have gamma 1 plus 3 alpha A equal to gamma 2 plus 3 alpha B. I want the value of alpha B. So 3 alpha of the container B equal to gamma 1 minus gamma 2 plus 3 alpha A. So to get the value of alpha of the container B or material of B, it is gamma 1 minus gamma 2 plus 3 alpha A whole divided by 3. You will get the value of coefficient of linear expansion. This is a simple example to understand this relation. We are given coefficient of apparent expansion in the two cases, in the two different containers. Then for one container we are given the value of alpha, for the second container we are finding, and here the basic principle is coefficient of real expansion of the liquid remains the same in any container. Coefficient of real expansion remains the same in any container. So that is the basic equation, application of this equation. Now let us move on to another application. As we in any general case, coefficient of real expansion is greater than coefficient of apparent expansion. Suppose in a container coefficient of real expansion is 3% more than coefficient of apparent expansion. Coefficient of real expansion is 3% more than coefficient of apparent expansion. What do you mean by this equation? Here coefficient of apparent expansion, suppose it is gamma A, gamma R 3% more. That means gamma R we can express as 103 by 100 into gamma A. Gamma R equal to 103 by 100 into gamma A. Now I want the coefficient of linear expansion of the container. I want the value of alpha of the container. Now let us substitute. Let us use the same equation. We can solve the problem in two ways. Here we can express the answer in terms of gamma A because problem is given in terms of gamma apparent. So let us first do it. Also we can express in terms of gamma R also. Let us, how it is possible. Considering this equation, gamma R, it is 103 by 100 into coefficient of apparent expansion, that equal to gamma A plus gamma of the container or gamma of the solid. So which indicate that coefficient of volume expansion gamma of the container is 103 by 100 into gamma A minus gamma A. Otherwise gamma of the container is 3, 103, taking LCM here, it is 3 of gamma A divided by 100. So this is gamma of the container. So if you take, this is equal to 3 into alpha of the container. 3 into alpha of the container. So if you take alpha of the container, that will be equal to, bringing this, coming here, it becomes 3 into gamma A by 100. Otherwise it is simply gamma A by 100. Gamma A by 100. So here we are taking the value of 3 alpha C. Gamma C is 3 alpha C. Gamma C we are getting like this. It is 103 by 100 into gamma A minus gamma A. So taking LCM 103 minus 100, it is 3 gamma A by 100. So alpha C, it will be equal to gamma A by 3 will be cancelled here. So that you will have gamma A by 100. Directly you can let us write here gamma A by 100. But now alpha C value. But if you want to express this value in terms of gamma R, if you write in gamma R, this will be equal to 1 by 100. Gamma A, let us express in terms of gamma R. So by cross multiplication, gamma A we can write as 100 into gamma R by 103. So when 100 is cancelled, you can also write as gamma R by 103. So alpha of the container we can express in terms of gamma A or in terms of gamma R also like this. So here we have calculated the value of alpha of the container in terms of gamma A or in terms of gamma R. Now let us take one more example, one more numerical. Suppose I have taken a liquid in a particular container A. In this container, for this container, coefficient of linear expansion is alpha A. I have measured the coefficient of apparent expansion for the given liquid in this container. The coefficient of apparent expansion, let us say it is gamma 1. I have taken the same liquid in another container B, where coefficient of linear expansion is alpha B for this container B. When measured in this container, coefficient of apparent expansion, let us say it is gamma 2. It is found that the coefficient of apparent expansions in the first container and the second container, they are found to be in the ratio gamma 1 by gamma 2 is equal to 2:3. Coefficient of apparent expansions are in the ratio 2:3. In the first one, it is gamma 1, coefficient of apparent expansion. In the second container B, coefficient of apparent expansion is gamma 2. But they are present in the ratio 2:3. What this equation indicates? Gamma 1 is the coefficient of apparent expansion in the first container. So you can write this as coefficient of apparent expansion. We can, from this equation, it is gamma R minus gamma of the container. Gamma of the container is nothing but gamma R minus, because we are talking about the first container A, gamma of the container is nothing but alpha A is the coefficient of linear expansion. So gamma becomes 3 of alpha A. And the second container, gamma 2 equal to gamma of the container minus gamma coefficient of real expansion minus gamma of the container. But gamma R is the constant in all containers. So gamma R will have the same value. But gamma C, here for the second container, coefficient of apparent linear expansion is alpha B. So the gamma value becomes 3 of alpha B. So these gamma 1, gamma 2 are in the ratio how much? Gamma 1 by gamma 2 equal to, dividing these two equations, this is in the ratio 2:3. The ratio of the coefficient of apparent expansions is 2:3 as per the given data. So very clearly, because alpha A and alpha B are given, coefficient of linear expansions of the two containers are given. From this equation, we can express the value of coefficient of real expansion in terms of alpha A and alpha B. Now let us go for the calculation. If you take the cross multiplication, it is 3 of gamma R minus 6 alpha A. That will be equal to 2 gamma R minus 6, this is 3 into 3, 9 alpha A, 3 gamma R minus 9 alpha A, it is 2 gamma R minus 6 alpha B. So we have 3 gamma R here, 2 gamma R here. Bringing this one this side, it is gamma R equal to, taking this minus 9 alpha to the other side, it becomes 9 alpha A minus 6 alpha B. So in terms of alpha A and alpha B, we can find out the value of gamma R directly from these two values. So here ratio of coefficient of apparent expansion is given. From the ratio of the coefficient of apparent expansion, we will get the values like this. So this is one more important model, numerical model related to the coefficient of expansion of liquids. Now let us move on to some other case. Suppose I have taken a liquid in a container. I have measured coefficient of apparent expansion and coefficient of real expansion, both of them. Coefficient of real expansion and coefficient of apparent expansion, they are found to be in the ratio 7:6. They are present in the ratio 7:6. Now I want the value of, let us calculate the value of alpha of the container first. Let us calculate alpha of the container. If the ratio of the two expansions, real and apparent, are in the ratio 7:6, we can express the value of alpha either in terms of gamma R or in terms of gamma A. In any way we can consider. So the two expansions, coefficient of expansion are the ratio 7:6. So you can say gamma R equal to 7/6 times gamma apparent. As per the standard equation, coefficient of real expansion is gamma A plus gamma of the container or gamma of the solid. So gamma of the container, it is gamma R minus of gamma A, coefficient of apparent expansion. Substitute values. Gamma R, if you substitute in terms of gamma A, gamma R we have expressed like this. It is 7/6 of gamma A minus gamma A. Because coefficient of real expansion we have taken from this equation. Gamma R equal to 7/6 of gamma A. So 7/6 gamma A minus gamma A, that is 7 minus 1. It is gamma A divided by 6. So coefficient of expansion of the solid, coefficient of volume expansion of the solid, it is gamma A divided by 6. Or if you want alpha of the container, it is gamma of the container by 3, it is gamma A divided by 6 by 3, it is gamma A by 18. Now we can find out the ratio of gamma of the container and real expansion also. So many factors we can calculate from this equation. Now first let us take the ratio gamma of the real coefficient of real expansion to the coefficient of volume expansion of the container. The gamma or gamma S. Here the ratio given is coefficient of real expansion and coefficient of apparent expansion. Now I am calculating the coefficient of real expansion of the liquid and coefficient of expansion of the container. So gamma R by gamma S. Let us substitute. It is gamma R, in terms of gamma A we got 7 gamma A by 6, and gamma S we got it as gamma A by 6 here. So gamma of the solid is coefficient of apparent expansion divided by 6. So this ratio becomes equal to 7. Gamma R by gamma S is equal to 7. Already here the ratio of volume expansion of the container and volume expansion of the apparent expansion of the liquid, it is gamma A divided by gamma S. If you consider, it is very clearly 6 here. So gamma apparent by apparent volume expansion of the solid, you are getting the ratio. You are also getting the ratio of coefficient of real expansion and coefficient of volume expansion of the container also. So by taking one ratio of these two, we are calculating the ratio of coefficient of apparent expansion to the coefficient of volume expansion of the container, and also coefficient of real expansion and coefficient of volume expansion of the container also. So this is one more numerical model. Right. Now let us move on to another one. Suppose coefficient of apparent expansion of a container, coefficient of apparent expansion of a liquid in a particular container is given as 5 into 10 power minus 5 per degree centigrade. 5 into 10 power minus 5 per degree centigrade. For the container, coefficient of linear expansion is given as 6 into 10 power minus 6 per degree centigrade. What is the coefficient of volume real expansion of the liquid? What is the coefficient of real expansion of the liquid? I want the value of gamma r. Coefficient of apparent expansion is given and coefficient of expansion of the container is also given. So gamma r I want. What is the value of gamma r is? It is gamma a plus gamma of the container, that equal to gamma a plus gamma of the container. I can write like 3 of alpha of the container. So let us substitute the values. Coefficient of apparent expansion, it is it is 5 into 10 power minus 5, 10 power minus 5 plus 3 of alpha c. Alpha of the container is given as 6 into 10 power minus 6 per degree centigrade. So this is the coefficient of apparent expansion, and this is 3 times alpha of the container. Then this is in 10 power minus 5, this is in 10 power minus 6 factor. So generally, if we do not follow carefully, we may commit a numerical mistake, mathematical mistake. So in such cases, to make it more convenient or easy to calculate, let us write like this. Because this is 5 in 10 power minus 5, let us multiply this with 10 and divide by 10, so that we can write this as 50 into 10 power minus 6 plus 3 into 6, 18 into 10 power minus 6. Totally it becomes 50 plus 18, that is 68. 68 into 10 power minus 6, otherwise we can write now 6.8 into 10 power minus 5 per degree centigrade. This gives the value of coefficient of real expansion of the container. Coefficient of real expansion of the liquid, coefficient of real expansion of the liquid. So coefficient of apparent expansion is given and coefficient of linear expansion of the container is given, and we are calculating the coefficient of real expansion of the liquid, which is the absolute property of that liquid. So this is one method. And in a similar way, we can also find out coefficient of linear expansion of one container is given. You can find out the coefficient of linear expansion of another container also. That is, I am taking a liquid where coefficient of apparent expansion in a particular container, let us say this is container A. For this container, apparent expansion is this is the 5 into 10 power minus 5 per degree centigrade, and coefficient of linear expansion is 6 in 10 power minus 6 per degree centigrade. In another container B, I found that coefficient of apparent expansion is 4 into 10 power minus 5 per degree centigrade. Coefficient of apparent expansion is 4 into 10 power minus 5 per degree centigrade. Now, I want the value of alpha of that particular container. Value of alpha of that particular container. Here alpha of the first container A is given. For the second container, we don't know the value of alpha. So we have to find out the value of alpha for the second container. Now, for two different containers, coefficient of apparent expansions are given, and we have to find out alpha of one container because alpha of other container is given. Then what is the basic equation we have to use? We said coefficient of real expansion of the container gamma r, it is the sum of coefficient of apparent expansion plus 3 times alpha of the container. Because this gamma r remains as a constant, we can use this equation for both the containers. So in the first container, using this equation, gamma r equal to, for first container it is 5 into 10 power minus 5 plus alpha, 3 alpha c I want, it is 18 into 10 power minus 6. That we have calculated as this, we can write this one is 50 into 10 power minus 6 plus 18 into 10 power minus 6, which is equal to 68 into 10 power minus 6. This is the value of gamma r we got for the as per the calculation with respect to container A. Now let us make the calculation with container B, but we have to remember that gamma r should remain as a constant. Gamma r should remain as a constant. Now applying this same equation for the second container, we know gamma r, it is equal to 68 into 10 power minus 6, but this is equal to the value of coefficient of apparent expansion in the container is 4 into 10 power minus 5. Otherwise it is, let us write here 4 into 10 power minus 5 plus 3 alpha of the second container B. Alpha of the second container B I want to calculate. So using this equation, this implies 68 into 10 power minus 6 equal to, let us write this as 4 into 10 power minus 5, let us write it as 40 into 10 power minus 6. So it is 40 into 10 power minus 6 plus 3 of alpha of the second container B. So very clearly 3 of alpha B equal to, subtracting this one and coming to bringing this to the other side, 68 minus 40, it is 28 into 10 power minus 6, or alpha of the second container alpha B equal to 28 by 3 into 10 power minus 6 per degree centigrade. So we can find out the value of alpha for the second container when alpha of the first container is given. The basic equation we are using here is the coefficient of real expansion remains as a constant irrespective of the container. In any container, gamma A may be changing, but gamma r always remains as a constant. So using this principle, we can find out the alpha of one container when the alpha of the other container is given. So like this, these are some numerical applications related to the expansion of the liquids and the basic equation, the relation between gamma A, coefficient of apparent expansion, and coefficient of real expansion. So based on that relation, we can have some numericals like this. So practice all these numericals once and try to solve the numericals available with you, so that with this one let us close today's session, and in the next class we will discuss more about the coefficient of apparent real expansions of a liquid and other applications of the expansions of the liquids. So let us close right now.